One last thing for velocity time graphs. We can actually get displacement directly from a velocity time graph if we're clever about it and we use a little geometry to our benefit. So let's take a look at the graph we looked at last time and this velocity time graph here. So this was a constant velocity. We know that because it's just literally a straight line. It's constant, right? We go 1/2 a kilometer per minute for 10 minutes. Okay, so now how far did we go? Now, if we did a displacement, change in position, velocity times time, right? So we did 1/2 of kilometer per minute times, what did we say, 10 minutes? So it says we get 5 kilometers. And not a shocker, the graph that this one kind of already told us that, 5 kilometers, right? But check out what we just did. 1/2 a kilometer per minute, that's this, right? 10 minutes, that's all of this. We basically multiply them together, which is basically finding the area of that shape right there. That's a rectangle. Base times height. That's it. So really, the area here under the curve, under the graph, under the, I'll say curve. This is not curvy, but curve is kind of a general term we're talking in mathematics. The area under the curve of a velocity time graph gives you displacement. In fact, if we went even further and took the whole 20 minutes, right, and included the area of this, guess what we'd get? 10. No! Wrong! Because all of this is negative. Why is it negative? Well, you're going negative 1/2 meter per second. This is actually a negative area. Why? Because you're going back the direction you came. Remember, this is finding displacement, not total distance, but displacement. When you look at displacement, it's only final position minus initial position. If you're in the same position, no distance. No displacement, I should say. No displacement. Okay, but what if our velocity wasn't constant? Let's say instead of that example, we looked at our velocity started at that 1/2 a kilometer per minute, and then it increased all the way up here to 2 kilometers per minute. Right? So we're speeding up. We're accelerating. And I'll ignore this second half. Let's not look at that right now. Let's just look at this part. Now, we have the original rectangle down here, right, that we just said was 5 kilometers. So we have that box, right? Now all of that was the initial velocity times time, right? 0.5 times 10, 5 kilometers. Now all of this up here, well, we could look at average velocity times time. That'd be one way we could do it. But we have a triangle now instead of a rectangle. Really, remember, the area underneath the curve is what tells us displacement. So if we want the area under this, we need the area of a triangle. 1/2 the base times the height. And for us, let's see, the base here is time, and the height is, well, that's V0, this would be V final. The height is the difference between those, so delta V. So I have 1/2 time times delta V. Okay. So that's the displacement for just the blue part, and V0 times T is the displacement for the green part. So if I want total displacement, let's make that red. So total displacement would be the green part, initial velocity times time, plus the blue part, 1/2 delta V times time. All right. Well, let's say I wanted to get that acceleration there because we just looked at the slope of velocity time graph and we said that acceleration is delta V over delta T. So if I kind of rearrange that, presto changeo, delta V is actually acceleration times time. Okay, I'm going to plug that in right here. All right, and there's method to my madness. There's reason I'm doing this. But so stay with me. Delta X equals green VT, which is 1 for the green part, and the blue part, 1/2 acceleration times time, because I just plugged that in for the delta V part, times time. You know what? And I can simplify that even more, because I have time times time is time squared. So acceleration times time squared. Now, I have a pretty useful equation that's going to be... Oh, look at the fancy rainbow pen. All right, don't get distracted, Mr. J. I can find total displacement, right, for anything starting at any initial velocity for any certain amount of time, as long as I know the acceleration. So if I know acceleration, I know time, I know the initial starting velocity, I can tell you how far it goes. This is going to come in super handy if you don't know what that final velocity is. It's going to kind of save us some steps, really. So, summarize. Area underneath a velocity time graph gives us displacement. And if we get clever about how we solve for that between the rectangles and the triangles that these shapes make, the area underneath, presto changeo, we get this formula, Vt plus 1/2 At squared, that gives us the total displacement as long as we know these initial things. So that's 6.5 minutes, and if you feel good about this, go on and go ahead. I figured, okay, we have a little bit of time. Let's do this example. And, where'd my thingy go? Come back. We'll zoom out a little bit and look at this example. And just kind of run the numbers for what we just made up here, just so we can see this in action. Okay, so total displacement is equal to initial velocity, which was 0.5, times time, which was for 10 minutes. I'm not going to worry about units right now just because with the marker gets messy. And then I'm actually increasing my speed part, so 1/2, let's get rid of this business, 1/2 acceleration. What's the acceleration? Let's see. Let's put that in here. Acceleration's delta V over delta T. So I went from 0.5 to 2, so that's an increase. Oops. That's an increase of 1.5. Stop moving on me. It's an increase of 1.5 over, 10 minutes. Gives me an acceleration of, go gadget calculator, 1.5 divided by 10.15 kilometers per hour, or kilometers per minute, kilometers per minute, because it's a velocity unit divided by a time unit. Okay, so that's my acceleration, 1/2 the acceleration, 0.15 kilometers per minute. Alright, let's skip the units right now, just for clarity's sake. And I said 10 minutes, right? 10 minutes. Squared. Now don't forget the square. That's the most common thing that people forget, and I tend to forget it too. Alright. Let's crank this out. Delta x, 0.5 times 10 is 5 kilometers, which, lo and behold, is what we went in our first example when we were just staying constant. Plus, we go a little bit more because we're speeding up. 1/2 times 0.15 is 0.075. And then 10 squared. Square it first before you multiply it by other stuff. 10 squared is 100. So I get, again, 5 kilometers blue plus 100 times this, so 7.5 additional kilometers is going to give me 12.5 kilometers total displacement. There we go.